In this video, we're going to finish off our main topic of reflection and refraction. Specifically here, we'll look at what refraction is. We'll also look at the related concept of dispersion. Let's start by reviewing the last slide in the last video, and that is the idea of rays and wavefronts. So if we have a wave moving to the right, we would represent that with a ray pointed to the right. But what this is really representing is a more complex thing, which is this wave. Remember that the wavefronts represent the crests of this three-dimensional wave. So the distance between each wavefront is simply the wavelength of the wave. In the last video I said, think about a wave that looks like this, but that is extended both in and out of the paper. And if you were looking at it from the top and you drew a line for each of the crests, those lines are the wavefronts. So we're going to use this concept to understand refraction. So what is refraction? Refraction is what happens when light moves from one material into another. And what we find is that when light goes from, let's say, air into water, the light bends at the interface between the two materials. And we want to understand why that is. Why does light have to bend when it goes from air into water or from glass into water, etc.? Well, this is where we're going to use this concept of rays and wavefronts. Here we've got light coming in. So here is the air up here, and here's our water down here. And our wave comes in, and what we find is that at this interface, the ray bends, and it bends towards the normal. Remember, here is the normal to the surface of the water and the air. So why is it that the ray has to bend? Well, the reason is that we know the frequency of a wave is determined by the vibration that creates the wave. Once the wave is created, the frequency doesn't change. But we also talked about in the previous video that the speed of a wave is going to be less in water than it is in air. Well, if the frequency doesn't change and the speed goes down, we can see that the wavelength has to become shorter. So you'll notice in the air, our wavelength is bigger than the wavelength is down here in the water. Well, the other thing that has to be true is the wave has to be continuous at the interface between the two materials. So in other words, if I've got a wavefront here, then I'm going to have a wavefront in the water at the same point, intersecting at that same point. And therefore, if the wavelength has to decrease, but the wave has to be continuous at the interface, the only way that can happen is if the wave changes direction. Again, remember that a ray and a wavefront are always perpendicular to each other. So the wavelength decreases, and therefore the ray and the light has to change direction. Let's continue to talk about refraction conceptually before we get into talking about Snell's Law, which allows us to figure out how much the light bends as it goes from one material into another. Let's look at the diagram on the left. Here we have light that is coming in the air, and so our incident ray is in the air. When that ray hits the water, two things happen. Some of the light is simply reflected back off the surface. So we always get reflection when light is hitting one material from another material. In this case then, if I call this theta 1, we know that this would also be theta 1. In other words, that's the law of reflection. What we're more interested in right now, though, is what happens to the light that goes down into the water. Let's call that theta 2. In this case, we know that the index of refraction of air is simply 1, and the index of refraction of water is 1.33. So you'll notice that we're going from a lower index of refraction to a higher index of refraction. When we do that, what we find is that the ray is bent towards the normal. In other words, theta 2 is going to be less than theta 1. The diagram on the right shows a similar situation, but now the light is originating down in the water and is coming out into the air. So once again, always some of the light gets reflected at the surface. So our reflected ray comes back down, and we know again that if that angle is theta 1, that angle is also theta 1, the law of reflection. Now, in this case, what we find is that theta 2 is greater than theta 1. So when we go from a higher index, 1.33 in this case, to a lower index, 1.00, the light bends away from the normal. So that's an important concept to have down, is just when we're going from lower index to higher index, the light bends towards the normal. When we're going from higher to lower, the light bends away from the normal. And also, just remember that there is always a reflected ray within the material that the light originated in. We now want to derive Snell's law. Snell's law is going to relate the angle of incidence to the angle of refraction. In other words, in this problem, we've got theta 1 is our angle of incidence, so our ray is coming down. It's bending right here at the interface, and this therefore would be theta 2. So we want to figure out what is the relationship between theta 1 and theta 2 and the index of refraction of the two materials, N1 and N2. In order to do this, we're just going to draw some triangles and use some basic geometry. The first thing that we have to understand is that if this angle is theta 1, then this angle here is also theta 1. So why is that? Well, remember that the wavefront and the ray are perpendicular to each other. But also, the normal and the surface are perpendicular to each other. Remember, this is the normal here. And so therefore, the relationship between this wavefront and the surface is the same as the angle between the ray and the normal. In the same way, this angle right here has to be equal to theta 2. So now I'm going to draw a triangle. I'm going to draw a line right here, which is perpendicular to the wavefront. Remember that that distance is simply the wavelength in material number 1. And then arbitrarily, I'm going to call this distance A. Let me write a trigonometric relationship between that. So this is a right angle. Notice that A is the hypotenuse. And so hopefully you can see that the sine of theta 1 is equal to the opposite side, which is lambda 1, divided by the hypotenuse, which is A. I'm now going to look at a second triangle. I'm going to look at this triangle right here. Notice that, once again, this is the wavelength in material 2 right here, and A is, again, the hypotenuse. So the sine of theta 2 is equal to lambda 2 over A. The next thing I'm going to do is I'm going to get rid of the A by setting each of these equal to 1 over A. In other words, the top equation, I get 1 over A is equal to sine theta 1 over lambda 1, and 1 over A from the next equation is equal to sine theta 2 over lambda 2. Therefore, I can get rid of that 1 over A by just setting those equal to each other. So sine theta 1 over lambda 1 is equal to sine theta 2 over lambda 2. Let me copy that on the next slide. Sine theta 1 over lambda 1 is equal to sine theta 2 over lambda 2. Now, ultimately, we don't want Snell's law to be in terms of wavelength. We want it to be in terms of the index of refraction. So again, we want it in terms of N1 and N2, and here's theta 1 and theta 2. So the next thing I'm going to do is I'm going to turn wavelength into velocity. I'm going to do that by multiplying both sides of the equation by 1 over f. Now remember, the frequency doesn't change. So the frequency in both materials is the same, and that's why I can just go ahead and use f without a subscript on it. We know that the velocity in material 1 is just the frequency times the wavelength in material 1, and the velocity in material 2 is the frequency times the wavelength in material 2. And so I can rewrite our equation now as sine theta 1 over v1 is equal to sine theta 2 over v2. The last thing that I'm going to do is now try to convert velocity into index of refraction. We know that the index of refraction is the speed of light in a vacuum divided by the speed of light in the material. And so if I just multiply both sides of the equation by c, so I can convert c over v1, since c over v is equal to n, is to just n1. So I get n1 sine theta 1, and c over v2 is n2. So I get n2 sine theta 2. And that is Snell's law. So we end up with a very simple relationship between the indices of refraction of the two materials and the angle that the light makes in the two materials. Now there's one really important thing to remember. Remember this in homework and on tests especially. The angles are measured with respect to the normal. So that's important. In other words, on a test, I might tell you the angle that the light makes relative to the surface. If you plug that into Snell's law, you're not going to get the correct answer. Make sure that you always use the angle relative to the normal. Another thing just to watch out for, you're going to want your calculator to be in degree mode because we're going to give these angles in degrees. Okay, let's look at the following problem. A beam of light strikes the glass of an aquarium at a 35-degree angle. What's the angle of the light beam with respect to the normal in the water? Okay, so we've got a 35-degree incident angle. Notice that I gave you the correct angle there. That's the angle with respect to the normal. And so let's first just kind of trace out what's going to happen. When we go from air to glass, glass is a higher index of refraction, so the ray is going to be bent towards the normal, and I'm going to call this angle theta g. I'm going to call this angle theta a for the angle in the air. Now, when the light gets to the next interface, we have to draw a new normal there. Now, when we go from glass to water, the angle is going to increase because we're going from a higher to a smaller index of refraction. And so as the light comes out of the water, it's going to bend away. And this is the angle that we want to find, theta w. Why don't you go ahead and see if you can apply Snell's law, n1 sine theta 1 equals n2 sine theta 2, and figure out what theta w is. Now, by the way, there's one thing you have to remember from geometry, and that is if you have two parallel lines and a line crosses them, this angle and this angle are the same. So you'll notice that this angle here is also theta g. Go ahead, pause the video and solve it on your own, and then see how you did. Okay, let's see how you did. So I'm going to write out Snell's law for the first part of the problem, which is going from air to glass. I'm going to write it this way: n air sine theta air has to be equal to n glass sine theta glass. So I could use Snell's law to calculate theta g, the angle in the glass. Before I do that, let me go ahead and look at the second part of the problem. Now I'm going from glass to water. You'll notice that now when I write down Snell's law, it's going to be ng sine theta g equals nw sine theta w. And so in fact, in this problem, you actually don't have to solve for theta g, because all we really care about is theta w, the angle in the water. You'll notice that since this side of the equation and that side of the equation are the same, I can conclude from that that na sine theta a equals nw sine theta w. Now, if you did go ahead and solve for theta g and then plug that in, obviously that's fine. You're just doing a little bit more work than you have to do in the problem. Okay, so now I'm going to go ahead and I'm going to solve algebraically for theta w. I get that sine theta w is na over nw sine theta a, or theta w is the inverse sine of na over nw sine theta a. And now I can just go ahead and plug in the values. Remember again, to make sure your calculator is in degree mode, we get 1 divided by 1.33 times the sine of 35 degrees. We've got 3 significant figures here, and so our answer should have 3 sig figs, and I got 25.5 degrees. Let's look at the following problem. Here we've got light that is incident in the water, so it's coming from the water. It's hitting the interface between the water and the air, and we're told that the incident angle is 60 degrees. So that's theta 1, and we're asked to find theta 2. So go ahead and pause the video and calculate theta 2 for me, and then restart the video. Okay, let's see how you did. So hopefully you did try this on your own, because I really wanted you to see the fact that your calculator gave you an error. Let's go through it together. I'm going to call N1 the index of refraction of water and N2 the index of refraction of air. And generally we use a 1 for the material we're starting from and a 2 for the material we're going into. It's also okay to use things like A or W for your subscripts if that helps you keep it a little bit clearer. In this case then, I'm going to write down N1 sine theta 1 is equal to N2 sine theta 2. And we're solving for theta 2. So sine of theta 2 is N1 sine theta 1 divided by N2, or theta 2 is the inverse sine of N1 sine theta 1 divided by N2. So now if you plug in the values that I gave you, so if we plug in 1.33 for the index of refraction of water, we plug in the sine of 60 degrees, and we divide that by the index of refraction of air, which is 1, what you notice is you get a value that is larger than 1. And that's why your calculator comes back and says error domain, because we know that for a sine function, the biggest that sine can ever put out is 1 or negative 1, and therefore the biggest number you can put in to inverse sine is 1 or negative 1. If you try to take the inverse sine of a number bigger than 1, you get an error. So what's going on here? Why did I want you to see that we get an error here when we try to do this calculation? Let's look at it conceptually in this way. Imagine that my light is originating in the water and coming out into the air. So this is theta 1, and this is theta 2. Well, we know already that in this case where we're going from a higher index of refraction to a lower index of refraction, that the light bends away from the normal. In other words, theta 2 is greater than theta 1. So now think about this question. What happens if we keep increasing theta 1? Well, since theta 2 is always bigger than theta 1, there's going to be a point where theta 2 is equal to 90 degrees. And when we reach that certain angle of theta 1, so that theta 2 becomes 90 degrees, then the light no longer can leave the surface. We call this total internal reflection because what we find is when we get to a value of theta 1 where the light would be coming along the surface, and really what that means is the light's not coming out anymore. So when theta 2 equals 90 degrees, we say theta 1 is equal to the critical angle. And for any value of theta 1 equal to the critical angle or greater, no light comes out of the surface. That's why we call this total internal reflection, because literally all of the light that comes up gets reflected back into the material. This is really kind of a bizarre thing if you think about it, because this interface between air and water is completely transparent. And yet, if my angle of incidence in the water gets too big, none of the light can come out, even though that interface is transparent. So it's a really kind of a weird thing. That's why we call it total internal reflection. Again, all of the light comes back down into the material. Let's figure out what is the value of the critical angle. What is that value for theta 1 where we stop getting light coming through into the air? Well, we can figure that out just by using Snell's Law. N1 sine theta 1 is equal to N2 sine theta 2. And I'm going to put in theta c for theta 1. And remember that the critical angle occurs when the light just stops coming out. That's when theta 2 has a value of 90 degrees. Well, you'll notice that the sine of 90 is 1, and so what we get is that sine theta c is just N2 divided by N1, or theta c is equal to the inverse sine of N2 over N1. It's important to understand that we only get total internal reflection when we're going from a higher index material like water to a lower index material like air. It doesn't happen the other way because remember then the light's bending towards the normal. If you plug in the values for air and water, what you'll find is that the critical angle for these two materials is 49 degrees. So if my angle of incidence, if this incident angle here is greater than 49 degrees, no light will come out of the water. All of it will be reflected back into the water. Let's look at a really important application of total internal reflection, and that is fiber optics. You've probably heard of fiber optic cables. It turns out that almost all of our data and communications that goes over landlines these days go over fiber optic cables instead of more old-fashioned copper cables. And so what are the advantages of fiber optic cables? Well, one advantage of fiber optics is that they can travel, or a signal can travel a long way in a fiber optic cable without needing to be repeated. Now, what is a fiber optic cable? It's just a thin piece of glass. And instead of using an electrical signal like we do in a copper wire, we use a light signal to encode the information, whether it's data or voice communications. So why is it that a tiny thin piece of glass can carry light over such great distances? The answer to that is total internal reflection. Imagine that this is an enlarged version of a fiber optic cable right here, and let's say that we've got light traveling in the cable, and that light gets up to the top of the cable here. Well, as long as the angle that it hits the side with is greater than the critical angle, that light cannot get out of the glass. It simply is going to bounce and come back down, and that will continue. So literally, even without putting any kind of a coating on this fiber optic cable, that light is trapped in the glass. And therefore, light can travel very far distances in fiber optic cables. So it's all about total internal reflection. Let's talk about our last topic in this video, which is dispersion. The first important thing to understand about dispersion is that it's related to refraction. In order to understand dispersion, we first have to understand a little bit more about visible light. When you see white light, what you're actually seeing is a combination of all of the wavelengths and frequencies that are visible to us. In this diagram, I show you the different colors for the different wavelengths of light. So down at the 400 nanometer wavelength, that's where we have violet. Up at the 700 nanometer wavelength, that's where red is. And obviously, if we're on either side of that, we get out of the visible part of the spectrum into ultraviolet or infrared. When all of these wavelengths are present, the wavelengths between 400 and 700, then we perceive that as white light. So white light contains all of the wavelengths in the visible part of the spectrum. So dispersion is what happens when we put white light through a material like glass, in this case a glass prism, and that light gets dispersed into the different individual colors. And so what we want to understand is, why is it that white light will break up or disperse into the different colors when the light goes through a prism? When we talked about refraction, we assumed that the index of refraction was constant for a given material. But it turns out that that's not quite true. The index of refraction varies a little bit with wavelength. So let's look at one of the more extreme examples, silicate flint glass. Notice that when we're down at the red end of the spectrum, the index of refraction is 1.61. But if we're way over here at the violet end of the spectrum, the index of refraction jumps to 1.66. Well, what that means is that the different colors will bend slightly different amounts because they are responding to slightly different indices of refraction. The reason that we use a prism to disperse light is simply because it gives us two refractions. So the light comes in, here's the normal. The light disperses a little bit, so red and blue ends of the spectrum are going to go a little bit, or not bend quite the same amount. Then we get another refraction, and therefore we get a greater spread. So that's why we use a prism to show this. Let's look at a fun example of dispersion, and that is, it explains why we see rainbows. So let's think about what happens when you see a rainbow. First of all, you'll notice a couple conditions have to be met. A storm that contains a lot of moisture has to have just passed. So the sun needs to be out. So here's the sun, and we've got sunlight streaming down. So this is the sunlight coming in. And then in order for this to work, so the sun's got to be behind you. Here you are down here. And you have to be looking towards where there's still moisture in the air. I want to focus in on a couple individual water droplets. So the sunlight comes in. We know that red and violet light are going to bend slightly different amounts in a material like glass or water. And so what I'm showing you here is that the violet light bends a little bit more than the red. Again, much like in a prism, we have refraction happening here. Here we just have reflection at the back of the water droplet, and then we have refraction happening again. So just like in the prism, we get two refractions, and that amplifies the effect. And so what we find coming out of the water droplet is the violet light is coming out up here, the red light is coming out down here, and of course all the other colors are in between those. So now think about what this looks like from your perspective down here. When you look in a direction towards this water droplet, the light that leaves that water droplet that gets to your eye is just the red part of the spectrum. However, this water droplet, notice the red light is, hitting your feet or something. But now the violet light from that water droplet is coming right into your eye. And again, this violet light is going above your head. So when you look in this direction, all the water droplets along that line are showing you red. And when you look in this direction, all the water droplets along that line are showing you violet. And anywhere in between, you see the other colors. And that's why you see a rainbow. Now, because this is a three-dimensional problem, we see an arc for the rainbow. But it's really just you're looking at the correct angle throughout that arc to see that particular color. Here's the final problem just to give you a little bit more practice. It says a light ray strikes a glass prism, an equilateral triangle. Remember, that simply means that all the angles are 60 degrees. At an angle of 30 degrees with respect to the surface of the glass. The light ray travels through the glass and into the water. What is the angle the ray makes in the water relative to the surface of the glass? So what I'd like you to do here is pause the video and try it yourself. Let me first just do the diagram with you just to kind of get you started. Here's the normal. And I'll just tell you how I'm going to label things. I'm going to call 30 degrees theta. I'm going to call this angle theta 1. I'm going to call this angle theta 2. Here I have another refraction. I'm going to call this angle theta 3. I'm going to call this angle theta 4 and this angle theta 5. Notice that it's theta 5 that I'm asking you to find, the angle the ray makes in the water relative to the surface of the glass. Remember also that we know this angle is 60 degrees, as is that angle and that angle. Okay, give it a shot, see how you do. Okay, let's see how you did. The first thing you had to realize is that you can't use that 30-degree angle that I gave you directly, because notice that's not the angle with respect to the normal. Therefore, the first thing we want to do is just figure out that theta 1 is 60 degrees, and that's the angle we want to use in order to figure out theta 2. So in other words, the index of refraction of air times the sine of theta 1 should be equal to the index of refraction of the glass times sine theta 2. And I'm just going to tell you what I got when I did that calculation. So again, theta 1 is 60 degrees. For theta 2, I got 35.3 degrees. Once I know theta 2, the next challenge is to find theta 3. Sometimes students will make an erroneous conclusion. They'll say, that's a right angle in this triangle right here, but you don't know that. You don't know what that angle is. What you have to do is work your way around the triangle where you do know the angles. So in other words, if theta 2 is 35.3, this angle here has to be 54.7. Since I know that this angle is 60 degrees, I can now calculate this angle. In other words, I know that there are 180 degrees in a triangle, and if I subtract the 60 degrees and the 54.7 degrees, what I'm left with is 65.3 degrees. So this angle is 65.3 degrees. Now if I subtract that from 90, I can find theta 3. So theta 3 is 90 minus 65.3, and therefore theta 3 is 24.7. Once I have theta 3, I now need to apply Snell's law again to find theta 4. So n glass sine theta 3 is equal to n water sine theta 4. And if you put in theta 3 of 24.7, you should find that theta 4 came out to be 28.1 degrees. And then, of course, to find theta 5 is just going to be 90 degrees minus theta 4. And therefore, my final answer was 61.9 degrees. Okay, that's the end of our look at reflection and refraction.